here. Okay. So, so we were looking at hydrogen atom problem using the Dirac equation, and so we'll just do a quick recap of what we did last time, and that is, of course, we are going to look at the Coulomb potential part of the electromagnetic field. We are going to set the vector potential to 0, and in that case, the potential term which is written out here, which is minus ZE upon R, is a new term compared to the free particle Dirac equation. And because the potential depends only on the magnitude of R, we kind of know using the central potential problems that there will be a rotational symmetry in this particular case, and as a result the angular momentum would be conserved. Since the potential is time independent, the energy is conserved, and parity is also a symmetry because the original Dirac equation was invariant under parity, and so is the Coulomb potential. So since the parity transformation squares to identity, parity would have, of course, plus minus 1 eigenvalue, and this is something we have already studied, say, in harmonic oscillator in non-relativistic quantum mechanics. So, but we will use this fact to classify states which are parity even versus parity odd. In the spherical polar coordinate system, which is what we will use, because if there is a rotational symmetry, then that is a coordinate system in which the problem becomes simpler. Parity transformation corresponds to R going to R, theta going to pi minus theta, and phi going to pi minus phi, phi plus phi, excuse me. Okay. And we have solved the spherical problem in non-relativistic quantum mechanics, and it would reduce to the same equation, and therefore the spherical harmonics, which are the eigenfunctions of the angular part of the problem, have the property that YLM change sign under parity transformation if L is odd integer, and they do not change sign if L is even integer. Okay. Then we have also tried to figure out what is the action of the parity operator on the Dirac wave function. Okay, and we said that like that would correspond to psi prime of R prime, where R prime is minus R piece, and we figured this thing out by studying the property of operators, and particularly Hamiltonian, which should have been parity invariant, that the parity operator should be proportional to beta, okay, such that Hamiltonian would commute with the parity operator. And so therefore the action of the parity operator on the Dirac wave function was P on psi of R is equal to beta times psi of minus R. Okay, so that is one thing that we realize. Okay, so as a result of all this, we said that like the simultaneously diagonalizable set of operators that we have in this problem is Hamiltonian itself, because energy is conserved. Total angular momentum J is Z component and parity. Okay. Since Dirac particle has spin half, we get J is equal to L plus or minus half, and if you fix the J value, then of course there are two different L values which differ by 1, and therefore a fixed J value, you have states of opposite parity. This is something we had already seen. Okay, then we said that we will employ the separation of variable technique even for the Dirac equation, and we wrote the wave function as a product of radial part of the wave function times the angular part of the wave function. And we decided just to kind of concentrate on the radial part, because the angular part is going to be some kind of YLM theta phis. Okay. Fine. So, but to be able to do that, we have to show that the Dirac Hamiltonian actually separates into the radial and angular pieces. And so therefore what we did was a few simple tricks to kind of segregate angular parts from the radial part. and that was one of them was to write r squared as alpha dot r times alpha dot r, and then use r squared alpha dot p to be alpha dot r times alpha dot r times alpha dot p, and then use alpha dot r alpha dot p piece and expand that using the property that alpha I alpha j is equal to uh, delta ij plus epsilon ij k alpha k, or sigma k rather. Okay, where sigma is the matrix that we had defined earlier. Okay, so we use that fact to simplify this r squared alpha dot p piece into r times alpha r, which is the radial component of the alpha vector, times I is bar r del r plus sigma dot l piece, which is the spin orbit coupling that uh, comes out naturally from the Dirac equation. Okay. Now, of course, one could write down this
So
more. Yes.
I still don't see why this breaks alpha r is not dependent on r. Like if we use the same representation that we were using initially, we defined as alpha as sigma in the off diagonal components.
Yes.
So if we write r dot alpha dot r, it will be x alpha x plus y alpha y plus z alpha z.
Alpha dot r.
And
Yeah.
uh, so in the off diagonal components, it becomes x sigma x plus y sigma y plus z sigma z.
Yes.
So how does it like break into yeah? So if we represent x y z in polar coordinates,
Yeah.
x is r uh, cos theta sin phi, cos theta cos phi, and y is r sin cos. Sorry, x is r sin theta cos phi, y is r sin theta sin phi,
Fine. Fine.
and
Yeah.
z is r cos theta.
Yes. Yeah.
So we'll get cos theta sigma z
Yeah.
plus sin theta sigma x plus sorry, sin theta cos phi
Yeah. So
sigma
what you
x
actually,
plus sin theta sin phi.
that is right. Yeah.
What?
So yeah. Please.
So yeah, so we'll get something that is still dependent on theta and phi.
No, so that is the point. So you need to use direction cosines. That's what I told you last time also. That you see, you are using locally orthogonal coordinate system. R theta phi are also orthogonal coordinate system locally. Okay. So what you are doing is the following: that you are looking at a particular uh, r vector. Okay, and orienting. So you take r vector in some direction in Cartesian coordinate system, and now you orient your polar coordinate system in such a way that r hat is pointing in that direction. Okay, if that is the case, then locally,
Okay,
curvilinear
yeah,
coordinates are orthogonal, so thetas and phi's are theta hat and phi hat are orthogonal to that, and therefore won't show up.
okay, yeah,
Yeah.
okay.
Okay,
Oh, I understood.
fine. So one could do the similar thing with alpha dot p, and you can write this expression as pr term, which is written as r dot p plus p dot r, to be uh, 1 over r del r of r. Okay, and use that expression to uh, kind of write down alpha dot p in terms of the r dot p piece times the spin orbit coupling. Okay, so that is another thing that one could do with alpha dot p factors. Okay, fine. So we used all this and plugged it back into the total expression, which was alpha dot p written as alpha r pr plus the um, spin orbit coupling plus the additional h bar factor because of this transformation, which we add into the angular part of the problem. Okay, so now we see that there is a radial part which is pulled out, then there is a radial piece multiplying the angular piece, but that is something we are used to, because even in the non-relativistic case, the angular Laplacian was multiplied by 1 over r squared part, and that's why centrifugal piece was L into L plus 1 upon r squared in the radial part. So here also we will solve this problem, plug in those values, and then take that as number, eigenvalue corresponding to angular part of the wave function, put it back here and solve this problem as a radial problem. So that's what we want to do. Okay, fine. Now Remember, this is something we had done in angular momentum algebra also, that if you have L dot S term, then you define the angular momentum J, which is L plus S, and then you say that J squared minus L squared minus S squared would be equal to 2 times L dot S. So you can replace L dot S kind of term in terms of J. Okay, so that is a kind of thing that we are doing here. We are writing J as L plus H bar sigma by 2, which is the same as the S operator we would have written down in the non-relativistic case. So then you can write down J squared equals square of the terms on the right hand side, which contains the dot product, and then you invert it. Okay, and only thing that I said last time also, that we use the fact that eigenvalues of sigma squared by 4 was 3 by 4. Okay, so that is the one which has been used here. Okay, fine, good. Now, of course, we need not the sigma dot L piece, but we need sigma dot L plus H bar piece. So that makes this factor go from minus 3 quarters to plus 1 quarters. And now we can just substitute the eigenvalues of these operators. And we find that if whenever J is L plus half, then sigma dot L plus H bar has a value L plus 1. And whenever J is L minus half, then the eigenvalue is minus L. Okay, I have forgot to write the H bar factor, but yeah, so there should be this times H bar and minus L times H bar. Okay, Mm. Okay, so clearly remember that uh, the wave functions that we had written down, they would have parity, which is based on what are the eigenvalues sitting around here. And for a fixed J, of course, the states would have opposite parity, and these quantities are also contributing in the same fashion. There are L values which are uh, separated by 1 up to a sign. Okay, magnitude is not important when you write minus 1 to the L, whether it is L or minus L, it doesn't matter really. Okay, fine. So then we looked at the square of this operator. Remember, this is already a scalar operator, so it's not like the operator J squared or L squared, but this is L dot S squared kind of operator. But nevertheless, if you look at the square of this operator, then you find that this operator can be written in terms of J squared plus H bar squared by 4, which implies that this operator would commute with J. Okay, that means you can find simultaneous eigenvalues of eigenfunctions corresponding to this operator as well as corresponding to J squared. Okay, fine. Now, of course, if you operate this in this particular form, then you would get the eigenvalue H bar squared times J into J plus 1. So if you can pull the H bar square out, you get J into J plus 1, which is J squared plus J plus 1 quarter, which can be written as J plus half squared actually. That's why the eigenvalues of this is just J plus half squared times H bar squared. Okay. So this is something we could use when we would start looking at the radial part of the problem. Okay, fine. So this is something I just said that they commute. Okay, but the operator actually doesn't commute with the Hamiltonian. So what we do is we define a new operator K, which is beta times L dot sigma plus H bar, and this is operator which commutes with the Hamiltonian. So I think I don't know whether that I have given as an exercise. Yeah, so it's kind of straightforward exercise. Okay, fine. Now you can check that because of this beta factor, the eigenvalues of L dot sigma plus H bar are kind of taking plus minus sign because beta would have plus minus eigenvalue. So therefore they would take plus minus J plus half. This thing here is a J plus half square piece. So therefore it will give you plus or minus J plus half thing. Okay, but you remember that J is already L plus S and S is half. So J was a half integral quantity and it starts off as plus minus 1, plus minus 2 and so on. Okay, fine. Uh, K equals 0 doesn't occur simply because the smallest value J would have is half. Okay, so let's come back to the radial part of the problem. Now, in that case, we have already replaced uh, the sigma dot L plus H bar piece by uh, the H bar times K operator, and then we have replaced the k operator by its eigenvalue small k. Okay, but that whole thing was multiplied by alpha r, whereas k was not there. In fact, we had only sigma dot l plus h bar piece, so we just multiply by beta square, one soaked up in k and the other is sitting around here. Okay, so this is the problem that we have to solve, which has complete radial dependence and no angular piece sitting around. Okay, good. So the radial part of the wave function, we will write it in two component spinor form. There's a 1 over r factor we have pulled out, and we want to solve for gr and fr essentially. Okay, good. This 1 over r factor is the same thing that you use when you uh, use the spherical polar coordinate system Laplacian. Uh, if you want to kind of make it look simpler, uh, have a multiplying factor 1 over r, which will make that Laplacian become simpler. Otherwise, it is like 1 over r squared del del r squared del del r kind of stuff. Uh, would kind of can be brought into a simpler form. Okay, we made one specific choice of alpha and beta matrices, and if you use that, then then you can write down these equations in this particular form. Okay, and we discussed this last time also, that we choose alpha this way so that you can get rid of I in the differential equation, and then everything that is there in the equation are all kind of real coefficients. Okay, so as I said in the last lecture, that we will study the singularity structure of these equations to solve. Okay, now in this particular case, the problem is quite simple, so we can just do it quickly. You notice that as r goes to 0, the coefficients would diverge. Okay, and as a result, you would deem r is equal to 0 as a singular point because the coefficients are diverging. Okay, now what you do is you do yet another transformation of in this equation, and this transformation is done in the following way. You define 1 over r is equal to rho. Okay, then minus 1 over r squared dr is equal to d rho. Okay, so if you use that to replace del del r by del del rho, okay, but when you do that, then you'll find that you'll have a factor of rho squared in the numerator. Okay, so you need to divide on the whole thing by rho square, so that the coefficient of the derivative piece is independent of okay. I mean, usually whatever you differentiate with is called an independent variable. So we want the coefficient of highest derivative piece not involve any function of the independent variable. Okay, but if you do this transformation, r is equal to 1 over rho, or 1 over r is equal to rho, it's the same thing, then you get a rho squared df by d rho kind of expression. So you divide whole thing by rho squared. But 1 over r will be written as rho in the numerator. But if you divide by rho squared, you get a rho downstairs here, rho downstairs here, and a rho squared downstairs here. Okay. Now r going to infinity would correspond to rho into 0. Okay. And then you find 1 over rho squared sitting here, e minus mc squared divided by 1 over divided by rho squared, z is squared by rho, and then there is no rho here, just derivative with respect to rho, and then there is a rho in the denominator here also. So you find that rho into 0 is again a singular point. Okay. So what we find is that not only r equals 0, but r is equal to infinity is also singular point. Okay, fine. So now we need to ask, what is it? Is there a difference between a singular point at r equals 0 and r equals infinity? Okay, and that is done in the following way. Okay, since this is a first order differential equation, actually it is not, but the way it is written, it is a first order differential equation. Uh, the reason why it is not a first order differential equation is the following, that uh, these are kind of coupled equations. So if you differentiate the first equation by r, okay, you take the ddr of the whole thing, then you find that you get a second derivative of f here, and a first derivative of g here, and a first derivative of f here. Okay, so but the first derivative of g can be replaced by these quantities. Okay, so dg by dr can be written in terms of this times f and this quantity times g, You can plug it up there. Okay. Of course, when you take a derivative with respect to r, you differentiate this quantity also. But nevertheless, after you do this substitution, you get terms which are like second derivative of f plus quantity involving f plus quantity involving g, and there is a first derivative of f. But first derivative of f again contains a term which is g and f. Okay, so if you substitute that, then you can kind of get rid of the g factor, and entire equation could be written in terms of f, and that would be a second order differential equation. Okay, so the reason why we see this in the first order form is simply because we have converted the second order equation into a matrix equation. That is why it looks this way. Okay, but nevertheless, let's not worry about this aspect. When we'll talk about differential equation, we'll talk about ordinary second order differential equation and discuss the singularity structures there. But in this particular case, let's look at the first equation. The situation with the second equation is identical, so it doesn't really matter. Okay, so you look at this equation and then you say that the coefficient of the highest derivative piece is can be set to 1. Okay, that was equivalent to dividing the whole thing by h bar c, or redefining f to f tilde, which is h bar c times f, whatever you want to do. Okay, but once you do that, then you have this coefficient 1. Now you look at the remaining pieces. Okay, and then you find that as r goes to 0, the coefficient of sitting in front of g diverges, and a coefficient sitting in front of f diverges. Okay, since it's a first order differential equation, you have to ask the following question, that if I multiply this coefficient of g, which is divergent, okay, and the coefficient of f, which is divergent, by r, okay, strictly speaking, you should multiply by r minus r naught, where r naught is the location of singularity. But since location of singularity is at r naught equal to 0, you just need to multiply by r, okay, in this particular case. Now, so you take this equation and you multiply this coefficient by r and this coefficient by r and see what happens. Okay, so what you get is something like this. You get r times e minus mc squared plus ze squared, and you get h bar c times k here. Okay, now once you get this, then you ask a question. Now if you take r going to its singular point, r going to r naught, in this particular case r going to 0, are these quantities singular? Okay, and clearly, as you can see, that these quantities are not singular in this case. Okay, is that fine? I'm saying mostly in words because I haven't typed all that stuff, but in the differential equation case we'll do it.
Sir,
Yes, yes, please.
is it like finding the order of the pole of the singularity? If you
Sorry, I
multiply
couldn't
it
hear.
by r minus r naught.
Sorry, I couldn't hear things properly, but I suppose what you're asking is that you are. Oh, my internet connection is not proper. Okay, can you hear me? Hello.
Yes, sir.
Okay. So I suppose what you were asking was that you basically try to find out the singularity structure and then multiply by appropriate powers. Is that the thing?
Yes, sir.
So yes, that is
Maybe we
what.
are finding the order of the pole.
Yes, yeah, yeah. That's what we are trying to find. Okay, but in this particular case, you have only first order equation. That's why it looks simple. Uh, if you have second order or higher order equation, you'll have to define it in a little more refined way. But exactly this. Okay, that's what we are doing. So what we find in this particular case is that you get a factor r multiplying e minus mc squared. There is no factor multiplying ze squared, and there is no factor multiplying here. Okay, you just h bar c k. Okay, so therefore, as r goes to 0, these new functions are well behaved. Okay, fine. So is this okay?
Yes, sir.
Okay. So if these functions are well behaved at a particular singularity, when you multiply them by 1 power, okay, of, and I'm multiplying by 1 power because it's a first order equation. Okay. If you do that and if you find them to be finite quantities, then you say that this singularity is a regular singular point. Okay, that is the name. That singularity is called regular singular point. Okay. If it is not like that, if you still find that it is singular, then you call that as irregular singular point. Okay. So as you can clearly see that this equation has r is equal to 0 as a regular singular point, because you take this, multiply by r here and multiply this function by r, and they are all finite as r goes to 0. Okay. Contrast this with what you would do at r equals infinity. Okay. Now for r equals infinity, as I told you that you substitute r is equal to 1 over rho, and then you get a rho squared df by d rho kind of stuff, and you divide the whole thing by rho squared. Okay. Then what you get is an expression like this. You get e minus mc squared upon rho squared plus ze squared upon rho plus the whole thing is multiplied by g h bar c del df by d rho plus h bar c kf upon rho. Okay, that is the expression that you would end up with. Okay. Now notice that unlike this expression, the expression in terms of rho is almost the same, in the sense that there is a 1 by rho here and a 1 by rho here, but there is a 1 by rho square sitting around here. Okay. Now when r goes to infinity implies rho goes to 0. Okay. So you try multiplying this expression by rho again, because it's a first order differential equation in rho again. If you multiply this expression by rho, then you find that this quantity is not singular, because there was a, you multiplied by rho and it eliminates a rho here. This piece is also not singular, but this piece is. E minus mc squared upon rho is the quantity which will be sitting around, and therefore as rho goes to 0, which is equivalent to r going to infinity, there is a piece which is sitting, which is in the coefficient of g, coefficient function of g, which diverges. Okay, and therefore this equation, uh, the singularity has a singularity at infinity, which is not a regular singular point. Okay, because regular singular point would have been just multiply one power and it should become fine. Okay, for the first order differential equation, and it doesn't happen at infinity, so therefore it is not a regular singular point. And if that is the case, then it is defined as an irregular singular point. Okay, so irregular singular point definition therefore is basically that anything which is not a regular singular point is an irregular singular point. Of course, it has to be a singular point to start with. Okay, so what we find is that r equals 0 is a regular singular point and r equals infinity is an irregular singular point. Okay, and
Sorry, regular meaning you can remove it by multiplying something.
no, no, no. Regular singular point, yeah, yeah. I mean, well, if you can remove the singularities of the coefficient function by multiplying by appropriate powers of r minus r naught or x minus x naught, then you would call that as a regular singular point. Okay. What is the power that you need to use is related to the order of the differential equation. Okay. Not a random thing. Okay. So, like for example, if you have a first order differential equation, then you can multiply only by first power of that quantity, say r minus r naught. But if you had a second order differential equation, then you, depending upon which terms you are looking at, either it is first order piece or second order piece. Okay, that is how it is analyzed. Okay, is it fine?
Yeah.
Okay,
So we
yes.
are checking this similarity for both these two equations simultaneously.
Well, you can do it simultaneously. It's a coupled equation. So you can do this study simultaneously for this, or you can convert this equation into a equation of for f only, and then study the similarity structure of that.
I mean,
Either
I
way,
was asking this because when you are looking at these two equations independently,
yeah,
then we don't know what G is. Like when we are finding similar, if there is any similarity for the first equation.
yeah, yeah. But we are not worried about the equation. We are worried about the coefficient functions in the differential equation, whether they diverge or not. What happens to
Yeah.
f and g is not our worry right now.
No, but let's say uh, if we were only solving for f in the first equation,
Okay,
and g was some function that goes as r raised to let's say r square.
Okay,
then there was no similarity in the first
that
place.
is right. That is right. But that is not the way you are going to solve, right? You are going to solve this coupled system. Okay.
Yeah, that's why I'm asking if we have to like look at similarities simultaneously.
Simultaneously, yeah. So we looked at the similarities simultaneously. Although I talked about the first equation,
Yeah.
second equation
Mm.
has the same property.
If there was similarity in the second equation and we couldn't find any similarity in the first equation,
Okay.
then that similarity would still be there
Yes.
because uh, it is in one of the equations.
Yes. Exactly.
Yeah.
Exactly. Okay. So as long as any one of the equation has that singularity which you cannot get rid of, you would say that point is singular point.
Mm.
Okay.
Okay.
And in fact, also I should say one more thing, that in this particular case, since we have two functions sitting around here, suppose you found that you multiply this function by r, okay, and it became finite, but you multiplied this function by r and it did not become finite, then you would still say that r equals 0 is a singular point. Okay, so all the terms have to kind of become finite. If not, then you would classify that as a singular point. Okay, and in this particular case, whether it's a regular or irregular singular point, depending upon how they behave. Okay, is that fine?
Yeah.
Okay, so uh, now there is a theorem for regular singular points. Okay, in other words, if you have a differential equation with regular singular point, then we know all the solutions around that point. Okay, there is no scope for imagination. There is a theorem which tells you exactly what would happen are in the neighborhood of that singular point. Okay, uh, and the situation about irregular singularity is exactly opposite. You really don't know anything about what would happen in the neighborhood of irregular singular point. And the reason is kind of simple, because while the regular singular point is a very constrained setup, that you have to have a very specific kind of singularity and you multiply by a specific kind of function. Hello, can you hear me?
Yeah, it got cut for a second.
Yeah,
So
yeah, because it also stayed unstable for me. That's why. Okay, so let me go step back a little. And so what I was saying, that like the regular singular point situation is a very constrained stuff. It has to have a very specific kind of singularities, such that if you multiply by a specific kind of function, all these coefficients functions become finite, regular around that point. Irregular singularity just says that, like, after multiplying in a very specific fashion, the coefficient function continues to be singular. Now that is saying nothing actually. So imagine that, like, instead of having z squared by r, suppose you had z squared by r to the 100. Okay, well, that would also be irregular singular point, and if it was r to the 2 also would have been irregular singular point. So so how bad a irregular singular point can be, has no kind of classification, and therefore it could be arbitrarily bad. Okay, and in that sense, there is no clear uh, method, for generic irregular singularity, uh, that you can use and say that, like, okay, it is going to work. Okay, of course we will study a method, but that method is a kind of, you know okay, maybe we can wait till Saturday. But that
no,
method is kind of something where you uh, keep kind of killing the dominant contributions to divergent terms, and keep getting more and more accurate solution in a kind of systematic fashion. We will see that. Okay, maybe not on Saturday. It may take more time actually, but let's see. Okay.
so also you said that in order to remove, like, let's say r equals 0, we are only allowed to multiply it with r, like not r square or r cube to remove the
Yeah.
point.
Yeah. Exactly.
And the reason for that is because
Okay.
it's a first order equation.
No, in this particular, it's a first order equation. If you have a second order equation, then you could have an equation which is like this. It is d squared f by dr squared with coefficient 1, okay, or constant coefficient, which doesn't matter really, plus some function, say let's call it p of r, times df by dr, plus some other function which is q of r times f is equal to 0. Okay, So you get two functions. One is a P of R multiplying the first derivative term, and Q of R multiplying the zeroth derivative term. Okay. In this case, you would do the same analysis would be done in the following way. Suppose R is equal to R naught is a singular point generically. Okay. Then you ask a question: is P singular at R equals R naught, and is Q singular at R equals R naught? If answer is that no, it is not, neither of them are singular, then you would call it ordinary point. Okay. If any one of them are singular, then you will call it a singular point. Okay. If of course both of them are singular, you will call it singular point uh, anyway. Okay. So at least one of them has to be singular for it to be a singular point. Then because P is a coefficient of a first order equation, sorry, first order derivative, you ask, is R minus R naught times P a regular quantity at R equals R naught? Okay. And is R minus R naught square times Q is regular? And if the answer is affirmative to both of them, then you would say that that point is a regular singular point for the second order differential equation. Okay. Now, if you think about it for a moment, you will realize one important thing, that in the neighborhood of a singularity, okay, I hope you can kind of visualize the equation. Uh, the first term is the second derivative of f with respect to r. Okay. Then in the neighborhood of r, singularity r equals r naught, if r minus r naught times p is regular, okay, that means the behavior of p in the neighborhood of r minus r naught at worst can be 1 over r minus r naught, right?
Yeah.
Because it could be well behaved also. In that case, of course, it can be just a polynomial function. There is no issue with that. But worst singularity that it can have is 1 over r minus r naught. Okay, that quantity is multiplying df by dr. Okay. On the other hand, q of r is multiplying f, and we are saying that is r minus r naught square times q of r is well behaved. And if the answer is yes, that means q of r, the worst behavior of q of r is 1 over r minus r naught square. Okay. Is this point clear?
Yeah.
Okay. So now you notice one thing, that the first term is a second derivative with respect to r. Second term is 1 over r times df by dr. And the third term is 1 over r squared times f. Okay. If in the neighborhood of the singularity. So that means in the neighborhood of the singularity, if you take r going to lambda times r, then you just get a 1 over lambda square factor out. Okay. So in the neighborhood of a regular singularity, the differential equation has a scaling property. Okay. That is the way the regular singular point is defined. Okay. And that is why specific powers multiplying it. Okay. Is the point clear?
Yeah, I was just thinking
Yeah.
that even if P and Q had a higher order thing, let's say P was divergent with respect to 1 by r minus r naught square.
Yeah.
So then it is not regular by this
Yes.
construction.
Exactly.
But we can still have f something like polynomial in r minus r naught, admitting a Taylor series around r naught such
No.
that it starts with r minus r naught cube or something.
No. 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 You can't. We will see when we'll do the differential equation. You'll see that the behavior of the equation is quite different actually.
Okay.
So, so I mean, one would think that if it goes like this, you could just take a function starting at higher power, but it's not true.
Yeah, I was thinking polynomial higher order. So
No, no, it wouldn't work actually. In fact, forget about the that kind of singularity. Even if the point is a regular singular point, a Taylor series is not necessarily a solution. In fact, most often it is not. Okay. Uh, of course, the problem that we are going to solve for as a hydrogen atom problem, it is a kind of slightly modified Taylor series, and it works. But generically, if you have a regular singular point, then you get a solution which is what is called a Frobenius series. Okay, Frobenius series is almost like a Taylor series except for additional piece multiplying the Taylor series, and that additional piece may have a fractional power of the argument. So in this particular case, you may have r minus r naught to say some sigma, okay, or some some power, and that sigma may not be an integer, it can be a fraction. Okay. uh, what happens in hydrogen atom is that that sigma turns out to be an integer. Okay. But that is just a fluke, it is not guaranteed that this is how it would happen generically. Okay. In fact, many differential equation in the neighborhood of a regular singular point don't have integer power, and it is in fact good that they are not integer powers from the physics point of view. Okay. So we will study this Frobenius theorem as well as the Frobenius solution to the in the neighborhood of regular singular point. The interesting thing about the Frobenius theorem is that it says that whatever solution, remember you are solving a differential equation, and differential equation means that when you say df by dr or dg by dr, that means you say that g at r plus delta r minus g at r divided by delta r, and then delta r going to zero limit. That's how the derivative is defined. So that means all these differential equations are carry really local information. Okay. And therefore they may not give you a solution which is globally well defined. Okay. In the neighborhood of singularity you may get a good solution because it's a differential equation you can solve there. In the neighborhood of a regular or ordinary point you can also get a good solution, because in the neighborhood of ordinary point Taylor series is a good solution. Okay. And then you can try patching all these solutions to get a full global solution. Okay. That is the kind of structure that one may have to use if the equation is just too complicated. But Frobenius theorem says the following thing, that if you have a regular singular point and if you find a solution in the neighborhood of the regular singular point, which you in principle can obtain, okay, uh, it may be a little complicated process, but it's a very well defined process, and you can obtain solution using that process. Then the Frobenius theorem says that the radius of convergence of that solution is at least, by the way, it's at least as much as the distance to the nearest singularity. Okay. So suppose you have a singular point at r equals 0 and r equals 1 and r equals infinity. Then your solution at r equals 0 is valid up to r equals 1 minimally. So the radius of convergence of that solution is 1. Okay. Similarly, a solution at r equals 1 would have a radius of convergence 1, because r equals 0 is about a distance 1 from there. Okay. But in this case, we have singularity at r equals 0 and r equals infinity. By the way, Frobenius theorem doesn't care about what is the status of the singularity. Okay. That singularity may be a regular singularity, it doesn't care. But a solution in the neighborhood of a regular singularity is valid all the way up to the location of the nearest singularity. So therefore, if you actually solve this differential equation in the neighborhood of r equals 0, that solution is valid all the way up to infinity. Okay. So in that sense, Frobenius theorem has so much power to actually allow you to get a solution, in this particular case almost globally defined. Okay. Now that is not guaranteed by the differential equation, as I said right in the beginning, because it carries only local information. Okay. So that is why Frobenius theorem is quite powerful. Okay. uh, Although in spite of it being very powerful, what we will do is we will actually solve the equation partly at infinity and then partly at r equals 0. Okay. And then combine the two pieces. Okay. In fact, there's something interesting that you can do, as I was saying in the last class, that suppose you take a harmonic oscillator problem in quantum mechanics, then that has a very interesting feature. It doesn't have singularity at r equals 0 at all. Okay. It is regular, it's an ordinary point. In fact, well, it's not called r, it's called x, one dimensional harmonic oscillator. So for any x, for any finite x, there is no singularity. All points are regular points, ordinary points, excuse me. Okay. uh, but it has a irregular singularity at infinity. Okay. So only one singular point. Okay. And normally what we do in quantum mechanics is to solve the harmonic oscillator near x equals 0 and solve harmonic oscillator near x equals infinity, and use those two pieces to patch them together to get Hermite polynomials and a Gaussian function and stuff like that. Okay. But in principle, what you could do is to just solve the solution only at infinity and still get the harmonic oscillator spectrum in spite of not solving the problem exactly. Okay. You can approximately solve the problem and still get the exact spectrum. Okay, very interesting thing that can be done with those kind of problems. Okay, but anyway, let's get back to what we were doing here, unless there are any questions about the similarity issue. Okay, so if there are no questions, then let's proceed. So let's, as I said, we will try to solve the equation in the neighborhood of r equals infinity first, and then we'll come back to r equals 0. Okay. Now at r equals infinity, uh, in some sense, you can kind of say that jd squared by r and h bar c k by r are the terms which are going to kind of fall off as you go to infinity, and therefore they are subleading, and you can just forget about them. Okay. Okay, and in that case, you need to just solve the equation by looking at the terms, which is e minus mc squared here, e plus mc squared here, and then forget about this two pieces and forget about these two pieces. Try solving. Okay. Now the life is even simpler because df by dr is equal to constant times g, and dg by dr is constant times f. So if you differentiate this equation, then you can just convert this into a second order equation either in terms of f or in terms of g. Once you solve that, you can put it back and get the other function. So if you solve for f, you can determine g from that. Okay. In this particular limit, it's quite easy thing to do. Okay. Fine. Okay. Now, one important feature that the solutions in the neighborhood of irregular singularity have is, besides something that I told you last time, and which is quite opposite of what the Frobenius solution would have, and that is that the solution has zero radius of convergence in the neighborhood of irregular singularity. Okay, so zero radius of convergence because you draw a disk around it, and that is the problem. This thing. But other important aspect is that in the neighborhood of irregular singularity, the solution typically has essential singularity. Okay. Now, by essential singularity, I mean the following: that uh, if you take the independent variable, in this particular case r, to infinity, then not only that the function goes to zero or the function diverges depending upon what happens. Okay, either function goes to zero or the function diverges. But not only that that this happens, but any arbitrary derivative of that function would also either go to zero or diverge. Okay, so in this particular case, what we find is that if you try to solve as r goes to infinity, then our solution has two forms. It could be either e to the plus ar or e to the minus ar. Okay, where a is this quantity. Okay, fine. So, so of course, we are doing quantum mechanics and we want square integrable wave functions. So we reject e to the plus ar. Okay, that is done by demanding physics. Okay, maths doesn't tell you. Fine. So you choose that. Okay, but you notice that as r goes to infinity, if you not only this function would vanish, but any derivative of this function would vanish. Okay, so therefore you would say that your solution has essential singularity at r equals infinity. Now this is a good behavior for us in quantum mechanics, but imagine if you had a plus sign, e to the plus ar. Okay, in that case, not only e to the plus ar would diverge, but any arbitrary derivative of e to the plus ar also would diverge at infinity. Okay, essential singularity has this feature. Okay, that arbitrary derivatives of the function would also diverge. Okay, contrast that with something where you had a behavior which was like as r goes to infinity, it goes as r to the some power n. Okay, then that also diverges, of course. Suppose n is equal to say 7. Okay, then it goes as r to the 7. But after taking 7 derivatives, all other derivatives, even 7th derivative is finite, and all other derivatives just go to 0. Okay, and therefore that behavior will not be called essential singularity, simply because after certain number of derivatives, the function would not be diverging. Okay, so you just do an expansion of the function, you find that there are divergent pieces at some point in that expansion, all other terms would be finite. Okay, that is not what would be called essential singularity. Okay, so this quantity is not very difficult to kind of guess. All you have to do is to kind of uh, if you put these factors back in, differentiate the first equation with respect to r and then use dg by dr up there, then you get e plus mc squared times e minus mc squared, which gives you e squared minus m squared c to the 4. And this function would have a h bar c factor sitting around. So you get kind of this expression. Okay. So a little bit of massaging and you can find that function sitting around. Okay. So, and in fact, this equation is very easy to solve because uh, it's a second order differential equation in f with constant coefficient. Okay. And you know that if you have a differential equation with constant coefficient, typically the answer to, the solution is an exponential function, e to the something. That would automatically give you a constant coefficient solution, which is what we find. Okay, good. So now, yeah, so these are the things I have already explained. Okay, so now let's look at what happens near x r equals 0. Okay, so I suppose I have time, right? It's just about 4. Okay, yeah, got a bit confused. Yeah, so let's look at r equals 0. And in the case of r equals 0, what we'll do is that we'll just define a new variable rho, which is the same a times r. Okay, and if you do that, then some of these terms in the equation can be made to look a little simpler. Okay, but at least the differential part of it is kind of looking better. Okay, so what happens is that you get an expression which looks like that. Instead of capital F's, I am writing small f's because I am writing them in terms of a new variable rho. Okay, so capital F of r is small f of rho and capital G of r is small g of rho. Okay, so something like that. And you get these equations, little bit of massaging with kind of arranging a factors of a correctly, you will get this equation. Okay. Now, as we have already seen that this equation has a regular singularity at rho equals 0. Okay. This rho is different from that r equals 1 over rho thing. Okay. Because that is different from this. This is just r is equal, rho and r are just related by linear relation. Okay. Good. So, as I said, because it is a regular singular point, the solution should be in the Frobenius form. Since rho is equal to 0 is a singular point, therefore we are expanding this in powers of rho to the n. Otherwise, we would have expanded as rho minus rho 0 to the n, where rho 0 was the singular point. Okay. Now you notice that this is an integer powers, okay, n going from 0 to infinity, fn rho to the n, pretty much like a Taylor series, okay, except that there is a rho to the s factor sitting outside. Okay, so f is equal to rho to the s times a kind of a Taylor series. Okay, uh, so okay, so this is what is called the Frobenius series form. Okay, and
Here S is not an integer
well,
necessarily, I mean.
yeah, a priori it is only a real number. Okay, what in our problem, of course, we get it as an integer, but generic differential equation, it is just a real number. Okay, so to put it little differently from complex, so one important thing about differential equation is the following, that although rho r all these variables are real, when you are trying to solve a differential equation, you assume that all these coefficients are complex numbers. Okay, they take complex values, you assume it that way. Then one of the reasons for doing that is that complex number field is algebraically closed, and therefore for every such equation you would have an answer. Okay, that is one thing. Second thing is, since you are studying singularity structure, it makes much more sense to look at it from complex analytic point of view than the real analytic point of view. Okay, and that is second thing. And the third thing is that, like, if you are studying solutions in the neighborhood of a singularity, you may have behaviors which are nicely explained in terms of complex variables than real variables. For example, suppose you write down f to be in this particular form, and suppose you find s to be, say, half, or some 3 by 4 or some such thing, right? Then you know that if you have a fractional power sitting around there, okay, then rho equals 0 is a branch point, okay, because of the fractional power. So this function typically has a branch point behavior in the neighborhood of a regular singular point. Okay, our problem is just too simple. Harmonic oscillator problem is just too easy. You don't even have a branch point. Okay, you just find that we will find that s is an integer. Okay, but that is that is a special case. Generic differential equation, you would find a fractional power. Okay, and that is, I mean, even in most of the physical situation, you want those powers to be fractional and not necessarily integer. Some of the simple quantum mechanics problems, of course, you get those to be integers, but that is the reason why they are called simple problems actually. Okay. Now, you may ask why same is here and here, okay? And the answer is it was not necessary, okay? You could have put S1 here and S2 here, or S and R or some such thing, and you could have substituted that. Then the leading order relation would have told you that S is equal to R, okay? I kind of took a shortcut by putting the same power here, okay? But if you want to do honest to goodness calculation, you should actually put different powers there. Okay, a few extra lines of calculation to arrive at this answer. Okay, then there is another statement that is written out here, that f0 times g0 is not equal to 0. Okay, this is just a statement of the Frobenius series, that the see that this series starts with rho to the 0. Similarly here, so that means the first coefficient is just f0. F0 plus F1 rho plus F2 rho squared plus F3 rho cube, and similarly G0 plus G1 rho plus G2 rho squared, and so on. Okay. So what we want is that neither F0 nor G0 is 0. Okay. Otherwise, you know, this is just a demand. For example, if it is 0, then what you could do is you could just shift S by S plus 1 and call F1 to be F0, and so on. Okay. Is that point clear? Let's suppose this series started with F1 row, F2 row squared. Then what you can do is you can pull a row out from everybody, convert this row to the S2, row to the S plus 1, call S plus 1 to be, say, T, and study the same thing again. Okay. So what this tells you is that the first coefficient, non-vanishing, implies that this power is fixed now. Okay. It cannot be shifted because these coefficients are non-zero. And this product is non-zero implies that both F0 and G0 are non-zero. Okay, that is a kind of efficient way of writing that they are both non-zero. Okay, so this is the Frobenius series form, and the Frobenius theorem actually tells you that, for a certain class of regular singular point, this is the kind of form of the solution, and that is it. You can't have anything else. All all you need to do is to determine what these S are and what these Fn's and Gn's are. Okay. I mean, it's not like very easy thing to do. Sometimes those equations may not be easily solvable, but the theorem definitely tells you that the solution is obtainable. Okay. There is one more uh, part of the Frobenius theorem which is not going to concern us, but if you find a kind of double solution uh, or identical behavior of both the solutions in the singularity, then you have a small correction to this form of the equation. Okay, when we'll do the differential equation, I'll tell you about that. Okay, so any questions about this? Okay, if not, then let's continue. So what we'll do is we'll take this form, we'll assume this form, plug it into these two equations. Okay, and look at what we get. Okay, so if you do that, you get these two equations. Okay, it's a bit of a mess, but nevertheless, you can check this. Okay, fine. So first of all, if you wanted, you could have just taken this row to the s inside, and you could have written this as row to the n plus s. The reason why one writes it this way is to kind of just make, at least uninitiated people feel good that this series is just an integer power series. Okay. uh, I mean, I think I also feel convenient writing it this way, but when you actually take the derivative, then it is Excuse me. But when you actually take the derivative, then it is actually, in that case, it is convenient to write rho to the n plus s. So this n plus s piece that you get here, it just effect coming from this derivative term, d by d rho. Okay, that is the piece that is going to pull down n plus s piece. K is of course part of the equation, which is sitting around there. Okay, here plus k and here minus k. So you'll see that two equations will have s plus n plus k versus s plus n minus k. Then there is just minus one piece which is kind of sitting around here, minus one. And then this piece is just coming down as it is. Okay, and you get these expressions. Okay, their powers are a little different because this is a constant coefficient, this has 1 over rho. That's why if this goes with gn minus 1, this will go with gn. Okay, so that's what you get, gn minus 1 versus gn. Simply because what you are trying to do is to look at the coefficient of rho to the n plus s minus 1 factor. Okay, and if you look at n plus s minus 1 factor, then these are the terms that you would get. Okay, and similarly here. Okay, now we want to solve this equation. Okay, now the system is still coupled. You have, in fact, little more complicated stuff because initially you had only f and g. Now you have fn minus 1, gn minus 1. But these are all numbers now. Okay, so we want to solve this. So the first thing that you do is to take n is equal to 0. Okay, so n is equal to 0 means basically trying to ask what f zeros and g zeros are. Okay, because if you take n equals 0, that's the only coefficient. Okay, solving that is what is called solving the initial equation. Okay, now given that product f0 g0 is not equal to 0, you know that the equation is non-trivial. Okay, in the sense that like what these two equations just reduce to these two equations. When you substitute f n is equal to 0, this just vanishes. This also goes away. You get this term, and similarly this term and this term. Okay. All other terms are subleading. They contribute not at n equals 0 level, but n equals 1 onwards. Okay. And of course, you substitute n is equal to 0 here. So you get s plus k f0 plus z alpha g0. And other one is s minus k g0 minus z alpha f0. Okay. And given the fact that both f0 and g0 are non-zero, okay, you can try to solve these two equations to determine what is the value of s. Okay, so that is the reason. So that's why n equals 0, the first in this sequence of infinite sequence of equations. The first equation is therefore called initial equation because it determines this index. Okay, and that's why it's called an initial equation. Once you determine that index, then only thing that remains is to determine these coefficients. Okay, is that fine?
We'll get to know s as a function of f0 and g0 as
Uh,
a sum.
no. It is independent of f0 and g0. Okay, so it would look like it is a function of f0 and g0, but it is not.
You just have to make the determinant 0, right? S plus k
Yes,
z alpha
yes,
minus z alpha and s.
exactly. You just write down a 2 by 2 matrix with f0, g0
Oh
as a
yeah,
column
yeah.
vector, and then you set the determinant to 0 to get the answer. So that doesn't depend on the column vector. Is that okay?
Yeah.
Yeah, okay, good. So, so because they are non-zero, you get this as a determinant, okay, and you get the answer s to be square root of plus or minus square root of k squared plus z squared times alpha squared. Okay. Now, I told you that the thing is simple and it doesn't look simple right now, but you will see in a moment that it is not as bad as it looks right now. Okay. But yes, this is a solution as of now. Okay. Fine. So,
What
yes.
was alpha here?
Oh, I didn't explain alpha. That's bad.
I
Yeah.
forgot. Is
It
that
is just
the
fine.
Compton wavelength?
No,
No.
it's just fine structure constant, E squared upon 4 pi. I don't know. That is bad. I should have introduced it at some point. Okay, clearly I have not done it.
Yeah, you told it about in the that case, Klein Gordon case.
Probably, but I think that's not the right thing to do. I will define it at some point again. Okay. In fact, right there, that may be a right place to say. Sorry about that. Uh, yeah. So this alpha is just you see our equation doesn't have e at all anywhere, right? That e squared factor will be now replaced by alpha, e squared upon 4 pi actually. So I just write that as z alpha. Okay, I'll just define it right below this. Okay, sorry for that.
Also, is this the solution for S, like below?
Yes, yeah.
K was the eigenvalue of that thing that we defined, L dot sigma plus
Plus h
H
bar.
cross. Yeah.
Yes, yeah.
And it goes from plus minus 1 to and so on.
Yes,
Even this restricts Z in some sense.
yes, exactly. So we will. That is our next statement. Okay, that that of course we are going to choose S to be positive. That you know why, right? Because if you choose S negative, then as rho goes to 0, F is going to diverge, right?
Yeah.
So therefore, you don't want singular solutions like that. You want wave function to be well behaved, right? So therefore, in spite of having plus or minus square root of something, we are going to choose only positive powers. Okay, and it's not like this is not the first time that we are doing this. When we solved the say Legendre polynomial equation, also we had a solution which went as uh, negative powers of arguments, and we rejected those simply because those wave functions would diverge at whatever x or z or whatever variable you use for solving Legendre polynomial as it goes to plus or minus 1. Okay, so regularity is a condition that we are going to use to choose a plus sign. Okay, the second thing is what Kaustubh was saying, that if you take the lowest possible value for k, that is plus or minus 1, then k squared would be 1. Okay, if you choose that, then that gives you a constraint on z squared alpha squared being smaller than 1. Okay, so our problem would develop instability at z alpha greater than 1. But this is a huge improvement over what Klein-Gordon equation had, because Klein-Gordon equation had a condition that z greater than what 69 was a problem. Okay, roughly. Okay, greater than or equal to 69 was a problem. But alpha is fine structure constant. E squared upon 4 pi is 1 over 137. Okay, so if z is greater than 137, then you have instability. Okay, but that is quite fine with respect to whatever we have observed so far, right? All atoms that we have seen have atomic number going up to like 120 or 125 now. Okay, they are still below 137, and therefore uh, Dirac equation definitely tells you that all the known atoms in the uh, in, at least on Earth, which are created in the laboratory, also some of them are still stable. Okay, there is no instability in this problem. Okay, so that additional factor of 2 uh, is the one which saves us here. Okay, is that fine? So yes, so this is a condition for stability of all the atoms that we have seen so far. Okay, so now we can kind of look at any one of these equations and write down f by g or f0 by g0 in terms of those variables, and then you can choose any one of them. You get s minus k upon z alpha. Okay, so that is one equation that you get. So now, of course, you could choose f0 to be 1, and then g0 would be kind of z alpha upon s minus k kind of stuff. It's up to you. Okay, remember these equations are linear, so therefore they can be scaled up and down by some factors. The solution doesn't change by doing that. That kind of liberty you don't have if your equation is nonlinear. Okay, so now if we can go back to these equations, okay, then what you could do is to Hello, can you hear me?
Yes, sir.
Okay, because it's again started saying unstable connection. Okay, so coming back to the recursion relation, you could multiply this first recursion relation by uh, e plus mc squared. So just give me a moment. It is, okay. Yeah. Okay, so here are the equations. So what you do is that you multiply the first equation by e plus mc squared, okay, and you multiply the second equation by square root of m squared c to the 4 minus e squared whole to the half, okay. So if you do that, then you have a e plus mc squared multiplying this piece. You have e plus mc squared multiplying this piece also. But if you notice that if you multiply by this in the second piece, then you get a e plus mc squared times fn minus 1 here also. Okay. So what we are going to do is to kind of multiply and subtract, okay, second term from second equation from the first equation. So if you do that, both of them have minus sign. So this term cancels with this fn minus 1. Okay. You can check that gn minus 1 also would cancel. Okay. It doesn't look obvious, but if you multiply by e plus mc squared, then you get e squared minus mc squared, which means this square root goes and sits upstairs. Okay, up to a sign, you get a minus sign because this is opposite of that. Okay, so you could take a minus sign out, write m squared c to the 4 minus e squared, and then write the square root in the numerator. Second equation doesn't have anything, but you're actually multiplying by this quantity. So therefore, this comes with a minus sign and a square root multiplying gn minus 1, it cancels. So what you have is two terms, one term involving e plus mc squared times this factor and a square root multiplying z alpha factor, which is multiplied by fn, and similar quantity for gn. Okay, it's just that they go opposite. E plus mc squared is multiplying this quantity, whereas e plus mc squared is multiplying z alpha here. Okay, good. So this is the equation. But what does this tell us? This tells us that if you know fn, you know gn. Okay, right? So it reduces our problem of determining only one of the two. Okay, if you determine fn, you determine gn automatically. What we have done so far is only determine the ratio of f0 with g0. Okay, which is this. Okay, good. So we want to ask a question: how do we go about solving this part of the equation? Okay, now uh, remember that this is the kind of, oh, sorry, let me keep this as it is. We are choosing this as a form of the solution and putting it in. Okay, now typically what happens is that if you take this as a form, plug it in, you can determine all fn's and all gn's by solving this kind of recursion relation. Okay, this or the other one that we are written down, which involves fn minus 1, gn minus 1 kind of stuff. Okay, it takes some effort to solve, but you can solve it. Okay, now the problem with this is that if you try to solve and set all, I mean, demand that all fn's and all gn's are non-zero, then you could ask a question as to what is the large row behavior of the final solution. Okay, the large row behavior, of course, will be determined by the large powers of row. Okay, and therefore fn with n large, similarly gn with n large. Okay, and if you look at those kind of behaviors of this function, then those, that solution in this particular case would go as e to the 2ar. Okay, that is what would be the behavior of the solution. Okay, now the reason why we don't want that is because if you take that as a solution, then remember we had obtained a solution e to the minus ar. Okay, we chose this solution because we rejected e to the plus ar, right? Because this is not normalizable. Now, if you keep this full infinite Frobenius series, then it will give you e to the plus 2ar. That will be multiplied by this choice at infinity that we have already made, and it gives you e to the plus ar, right? 2ar minus ar gives you e to the plus ar. And therefore, you will end up with the other solution which you had rejected. Okay. So, only way you can kind of avoid getting this exponentially growing solution from this Frobenius series, is to say that there exists some n is equal to n prime, okay, at which fn prime is just 0. Okay. So there is just some n equals n prime, so that, okay, I chose it this way, doesn't matter. That there exists some n prime, so that fn prime plus 1 and gn prime plus 1 just vanish. Okay. If you, hello? Yeah, so if you demand this, am I audible?
Yes, sir.
Yes, sir.
Okay, okay, good. So if you demand this, then your solution, this series is going to terminate at some power. And we know at which power it is going to terminate at when n is equal to n prime. Any powers about n prime plus 1, n prime plus 2 onwards are all going to be 0. Okay. Now, how do I know that higher powers are 0? Well, that comes from this recursion relation. Okay, maybe I just keep this here and just scroll this down from this recursion relation. That suppose a particular power, if n, say fn minus 1 and gn minus 1 are 0, then you can show sequentially that fn and gn also would be 0. And if fn and gn are 0, then fn plus 1, gn plus 1 also would be 0. Okay, fine. So what is the meaning of this? The meaning of this is that this solution, okay, is not an infinite series, but it's just a polynomial. Okay, and it terminates at some power. Okay, what is that power depends upon what is the solution that you are looking at. Okay, fine. So if you claim that n plus 1, n prime plus 1th power is 0, then nth power would have this relation. Okay, this relation is actually independent of this demand. Okay, because after subtracting these pieces, okay, so for example, you look at this expression, okay, and suppose you say f n minus 1 is fine, g n minus 1 is fine, but fn and gn are 0. Then these two terms go away and it tells you that fn minus 1 is equal to this quantity, okay, which is what this expression is. Okay, and since this relation is independent of n and n prime, it is true for any n prime. Okay, is this clear? If this term had survived, then the relation would have depended on choice of n, and therefore it wouldn't be valid for arbitrary n. Okay, so what we have found is that we have obtained another relation between fn's and gn's. Okay, is that okay? Fine. So I think what I'll do is I'll stop at this point, and what we'll do is that we'll use these two recursion relations and this condition to determine the spectrum of the theory. Okay, but that will be in the next class. Any questions?